So if we look at an element, so node 1 has position XA, node 2 has a position XB, and we're going to deform it, meaning we're going to change XA and XB, but we're going to do a real special type of deformation, right? And that's going to be that XA plus C0 and XB plus C0. So what kind of deformation is that? Rigid, right? So I said I'd deform it just to be general, but I deformed both nodes by the same amount, so I didn't actually change the length of my element. So it's just a rigid body displacement. I displaced the entire thing by C. And if I displace the entire thing by C, and no matter what the interpolation is in between, no matter what I choose to be linear, quadratic, whatever, the displacement field anywhere in between is going to be C, right? So since U1 is equal to C0 and U2 is equal to C0, then my entire displacement, or my entire, I guess in this case I said I'm deforming it, so we are talking about displacement, right? So my entire displacement field is C0. So right, so if and we know, so U of H is equal to C0 is equal to N1 U1 plus N2 U2, and if we plug that in, right, then that's N1 C0 plus N2 C0, okay? So if we divide both sides of this equation by C0, then I get 1 is equal to N1 plus N2. So we sort of proved that for any choice of n, because I didn't specify what n is. Well, I guess maybe in a way I did, because it would have worked anyway, but I sort of specified it because I only have two terms here. That means it's linear, right? But it would also work if I had quadratic and I had an N3 U3, it would still work out. So this is called a partition of unity. So that's the name given to this property. It's actually it's useful in a lot of things, and it forms the basis of so-called extended or generalized finite element methods. But aside from that, it can actually just be a useful way to check your code when you're writing your code. Once you write your shape function routines and you've computed them, if you're sort of unsure if they're correct or not, you can always just sum them up, and they better add to 1. The other thing that we said, or that we observed, is actually that if I take the ith shape function and I evaluate it at the j node, where I and j go from 1 to the number of shape functions, okay, or number of nodes, which are equivalent, then I get 1 is equal to j when I is equal to j, and 0 when I is not equal to j. Yeah, yeah. So I was going to ask that question, you know, does this look familiar, right? Of course, this is the Kronecker delta function. And so this is so-called Kronecker delta property. Okay? So we like interpolants that have the Kronecker delta property because it makes applying essential boundary conditions really easy, right? When we apply essential boundary condition, we're saying we're fixing, let's assume we're talking about displacement, right? We're fixing the displacement of the nodes to some value, whether it be 0 or u0, right? Whatever. We're fixing it to a value. So as long as I have something that has a Kronecker delta property, it makes it really easy because if I fix this to some value, since the shape functions pass through it, they have to conform to the boundary condition, or it has to work. Right? But if I had, say, a B-spline interpolation where you could have nodes that the shape functions don't pass through, and or you had a set of basis functions that don't exhibit Kronecker delta property, then you have to do something special when it comes to applying essential boundary conditions. Because in that case, you could have a node here, right? You could have a node here with nothing passes through, and you're fixing that node, but you're not forcing, since the shape functions don't pass through, you're not making any changes or causing the shape functions to conform to the position of that node, right? And so whenever, we like interpolants that have Kronecker delta property. And so, while we certainly, there are a vast number of interpolants, and for special cases, people use a lot of other ones. Generally, when people talk about the finite element method, they're talking about linear Lagrange polynomials. Linear Lagrange polynomials. So Lagrange interpolation, linear, that are just linear. And when people, so then later on, and we'll talk more about it, but later on we'll talk about H refinement. So H refinement is when you continue to subdivide the mesh, right? So H is like your characteristic element length. So you subdivide the mesh, that would be H refinement. P refinement we already did. We did it as an example in the Ritz method. P refinement is we go up in polynomial order, right? So H, think of characteristic element size. P, think of polynomial order. So when we talk about H refinement, we're going to add more elements. When we talk about P refinement, we're going to go up in polynomial order. Okay. And there's a whole class of methods called HP, in which you want to optimally change H and P together so that you get optimal spectral convergence, like as fast as you can get. And when I say convergence, I'm talking about convergence to the exact solution. We'll stop there.